So I just did a seminar the other day about this topic at university, and might as well put this knowledge somewhere. And I said knowledge, but then again, if I get something not completely right, I mean, look at the title, dude. So, cryptography, right? A way to keep your data safe, even if maybe some data leaks happen, maybe if it is some type of information that is bound to come in contact with third parties, to guarantee that they don't have access to what the data means, what information is conveyed by it. There are many ways to do it, and a lot of them are, realistically really safe to our current processing style of things, but quantum computers can actually kind of change that. But for it to make sense, just let's see some concepts of TOC. But we're keeping it simple though, right? We're keeping it dumb. So complexity classes are kind of like classes that define how much some problem takes of some resource, let's talk time here, to completely decide or solve any problem in relation to any input. So the problems are by the way, problems can be like algorithms to encrypt something or decrypt something in our case. These problems that can actually be solved in practical time, by the way, polynomial time, in the current state of processing, or which means our current machines can process them and solve them in realistic time, right? Practical time, are called problems of the class P. Problems of class NP have more than one definition, but I'm going to stick with one that says, imagine a machine that can have true, for real, legit, complete parallelism, right? It can go into all these different computational branches at the same time. Remember, our current machines, the classical computers, don't really have a true parallelism. Even the parallelism that we kind of have in practice is kind of just switching back and forth from different processes. So our current machines are completely deterministic, which means no parallelism. Non-deterministic machines are the ones that supposedly would have completely true parallelism, and those would be called non-deterministic machines, right? And the problems of the class NP are basically all the problems that can be solved with true, for real parallelism. All the possible computations happen at the same time, and that happening, you can solve or decide these problems in polynomial time. By the way, there is a deterministic definition using a certificate, but they're equivalent, and the first one makes more sense in this scenario. So just stick with the first one. So now that we know that there are problems that can only be solved with that non-deterministic approach, we know that there are some algorithms that can base themselves into these problems that can't really be solved by our current classical machines in realistic time. And some cryptography algorithms are based around that. Another side note, there is also NP completeness, which is basically the concept that there are some problems in NP that all the other problems can be reduced to them, which essentially means if you can solve those NP complete problems, you can solve just about any NP problem, which I'm not going to go too deep into, but it's pretty interesting, so I thought it was cool to mention. Alright, dude, but who cares though? Who asked, bro? Who asked? Hear me out now. So I'm guessing you know what bits are, right? Right, dude? Okay, you can represent different values based on zeros and ones. So if you have 4 bits, you agree with me that we can represent 16 different numbers, right? But you can only represent one number at a time with these 4 bits. The difference with quantum computing is they don't have bits, they have qubits maybe. And I'm going to simplify that so much, dude. But usually qubits use electrons and its spins to kind of define the values of a qubit, right? So the spin of it determines if it's 0 or 1. But, Schrodinger's cat, superposition, all that, you don't really know until you look at it if it is 0 or 1. So these quantum computers don't really look at the values as so much as they use equations with those qubits in mind without actually looking at their value, but utilizing the probability of the state of it in the equation. So basically, they use it without really knowing what it is, but using the probability of if it is 0 or if it is 1. So they don't really need to collapse. They just get the 2 coefficients and use in the equations. And because they have those 2 coefficients now, so what's really fucking cool about it, okay, cool is kind of out there, but what makes it real fucking interesting though is that because in the equation you are taking into consideration both probabilities. For each qubit, you are actually being able to represent two states at the same time. Same time, parallelism, non-determinism. So because of the, even if probabilistic parallelism that quantum computers can kind of emulate, and its similarities with the non-deterministic machines of TOC, we have that there exists a complexity class of problems that can be solved in practical time by these quantum computers, guaranteed to be greater than P, which is the solvable problems of right now in practical time. So if you've been connecting the dots, you can see that if there is some cryptography algorithms that are based into NP problems, all of a sudden we're going to have some new type of complexity class that is achievable for us that could actually solve the NP problem of these cryptographies, because before it wasn't really possible for them to be solved with our classical computers, but they can be solved in practical time, even if it takes a lot, by these new quantum computers. So some algorithms might be broken by it, and that is why quantum computers can break cryptography, kind of. Now, for disclaimer, to make it less cool, a lot of the cryptography algorithms are still not going to be broken, and even when some of them are, there are going to be new cryptography algorithms based on quantum computing, so maybe things get even safer. So yeah, that's it.